Hey everyone, thanks for tuning in. Happy Friday to you. This is another episode of the F Word Programming in Fortran. Today we're going to be talking about how to stabilize a nonlinear shallow water equation solver. If you remember from a couple weeks ago, we were working on a nonlinear conservative form shallow water equation solver using the discontinuous Galerkin spectral element method. Some things I didn't share with you the last time is essentially the conservative form of the nonlinear shallow water equations is not guaranteed to be stable. It also exhibits some issues when you start to have variable topography. In particular, you're not able to actually maintain a quiescent flow. So if you had variable topography and no motion to begin with, unfortunately, the conservative formulation that we came up with last week and implemented does not preserve that condition. And so I'll be showing you a little bit about some test cases that we put into self that demonstrate that particular issue. But in general, today's motivation is really focused on kind of stepping back just a little bit and really lining out some criteria we want to have for that shallow water equation solver. So particularly, we want a method that conserves mass and momentum. And I'll try to convince you here in the next couple slides here that the method that we did have to begin with absolutely does this at the moment. The problem is the semi-discrete form, just for the spatial discretization side, it unfortunately is not stable. And we'll talk a little bit about that today. And then, of course, the other condition we want to have when we develop a method is that it's going to preserve steady state solutions. So these are the three kind of topics we're going to hit on today. And after the whiteboarding session, I'll hop into the code and show you a couple examples where these are currently not satisfied in the 2D shallow water equation solver. Now, there's a lot of work that it really takes to get to a point where the 2D solver is meets this criteria, but we can demonstrate this with the 1D solver. So we'll be doing a nonlinear shallow water equation solver in 1D today to kind of demonstrate some of these points. So we can carry that work over into a 2D solver in the next couple weeks. So let's first talk about what we mean by mass and momentum conservation. And where we're going to start is with the shallow water system. And so this diagram depicts really what we're working with here. So we have the bottom topography is given by just if you were to think about the vertical coordinate going up and down here, we'll call that Z. The topography is defined on the bottom at z equals minus h, and the free surface height is allowed to vary with time and space. We call that eta of x, y, and t. And inside this fluid, we have velocity both in the x direction and in the y direction. But what we'll be working with today is in 1D. In the equations we're going to be starting with for the volume, we have the time derivative of the fluid height. So this is the difference between the free surface height and the bottom topography is just going to change due to volume flux divergences. And then the momentum equation. So what we're going to be tracking is the velocity integrated over over a fluid column. So we have advective fluxes that contribute to that, as well as pressure gradient forces. And on the right-hand side, we have a term that accounts for variable bottom topography. And what we mean by having momentum conservation is if you were to integrate the momentum equation over all of space, what you should end up getting is a statement that basically says the momentum is only coming in from the boundaries, and same thing with the fluid volume as well. And sure enough, at least on the fluid volume side, it's pretty easy to see if you were to do an integral over your model domain, and here is just in the x direction. Let me actually move this down. So if I were to, get rid of that, integrate over the model domain, let's just say the model domain is from 0 to 1 in the x direction. So we'll integrate 0 to 1 h of t dx plus 0 to 1 hu of x. I love doing 1D because it makes things a lot easier, of course. Then this should really address most of the problems that we have in the code currently. When you do this integral over space, of course, if you've done Calc 1 before, you already know right off the bat This second term here, this integral of a derivative over x, just gives us the value of that flux function at the boundaries. And so the amount of volume that comes into and out of the model domain is really just controlled by things that are coming in from the boundaries. And there's not internal sources that contribute to that. So we can come up with a similar statement for the momentum, where essentially momentum is brought into the model domain from the boundaries. And this is what we mean by having mass and momentum conservation. And at least so far, I've just been looking at the continuous equations. What we want to have in the discrete form is to preserve this particular property. Now remember, when we did the discretization for this system, which we'll walk through here just really quick, we made a couple assumptions. One, we're gonna write this system as a conservation law that looks something like this. So we have a vector of prognostic variables, these s's, and we have a vector of fluxes associated with those prognostic variables and some source terms. And in this problem, the source terms are coming from those topographic gradients. The fluxes are these terms here that are inside those derivatives. And of course, those prognostic variables are the guys right out front. Now, when we do the discretization, remember what we did was we said that S is a polynomial of degree n. So the way we write that is S is in that space of polynomials of degree n. F is as well. So we co-locate the fluxes with the solution variables. And even though, for example, like if I were to calculate h by u squared, if I were to think about calculating that if the variables I'm tracking were hu and h, what I have to do in the code, right, is to do hu, which is the variable I have access to, square that whole thing and then divide by h. That's really a rational function. And because if hu were a polynomial of degree n and h is a polynomial of degree n, I've got a rational function of polynomials here. So I actually incur an error by assuming that the flux function itself is also a polynomial of degree n. And this is a source of a lot of our misery in doing these kinds of methods in terms of ensuring that we have stability. But this, nonetheless, we choose this because this actually gives us a really nice and efficient approach towards developing a conservation law solver. And again, the same thing with Q there. We also cast Q as a polynomial of degree n. Okay. The other thing we're going to do, and in one dimension, it's very easy for me to draw as opposed to 2 dimensions. But if I have my whole model domain is from 0 to 1, what I'm going to do is divide that space into elements. So we have, for example, omega 0, omega 1, all the way out to the kth element. And inside of those elements is where I'm going to be representing the solutions as polynomial of degree n. Now the last thing we do is, instead of solving the equations in the strong form, which is what we have up here, where we keep derivatives on those flux functions, we put it in the weak form so that we can relax that smoothness criteria on the solution. So what this ends up looking like, to get the weak form for each element, we have ds dt multiplied by a test function, and I'll explain what that is here in a minute. We're going to integrate over each of those elements, so each omega k. So you have d omega k here. On that second term, if I multiply by that test function and I do integration by parts once to get the derivative off of the flux function, what I'm left with is the flux function multiplied by the test function, evaluated at the element boundaries. And for reasons that will become very clear, the element boundaries we evaluate at -1 to 1. And essentially what we do is each of these elements get mapped to a reference element that is on -1 to 1, and we actually keep track of those metric terms, which, you know what, I'm going to go ahead and do that right now. If I map each element to a reference element that's on -1 to 1, I can change the boundaries of this integral for every single one of these elements to be -1 to 1, and then that d omega k just becomes d, and I call it c. This is our computational coordinate. So that reference element's computational coordinate is c. Okay, and then we have, continuing with that integration by parts, we have minus the integral -1 to 1. We have the flux function multiplied by the derivative of the of that test function that we brought in. And on that right-hand side, we still have minus 1 to 1 q multiplied by test function dc with the delta xk on 2 right up front. All right. So that's step one. And so right now we have the solutions are polynomials. The test functions themselves also, we restrict this statement really, when we solve the weak form, we enforce this statement for all possible phi, and if you're doing this for continuous problems, this is all square integrable functions. But since we're doing a discrete problem, we actually restrict that space to just to be polynomials of degree n. So this must be true for all phi that are polynomials of degree n, and we can even specify the domain they exist on, minus 1 to 1. So that's what we want to have hold for every single element. Now, because what we're doing with this boundary term when we did that integration by parts is essentially evaluating the flux on the element boundary, so that would be like at these locations at the edges of each of the element. What we actually do in practice is replace this flux with what's called a Riemann flux. And a Riemann flux essentially is usually for these nonlinear problems an approximate solver that looks at the solution state on either side of the edge. So like if I were looking at this edge right here, I have a solution state on the left side, I have a solution state on the right side, and it's possible that those estimates of the solution don't actually match. And what you do with the Riemann solver is sort out the speeds that shocks move at, and then what the combinations of the prognostic variables that contribute to a particular shock moving at a fixed speed, and you basically apply an upwinding method. And this, in some sense, what happens in the end here is you get a little bit of dissipation added to your system so that the forward integration can be at least somewhat stable. And I mean, hopefully it is stable in the end. And so all we do here is notationally is we just replace that f with f star to indicate that it's a Riemann flux. Now this statement here for all phi in Pn, what we can actually do is we just need a basis, so a set of functions that all other polynomials of degree n can be described as. And the easy way to do that is just to pick Lagrange interpolating polynomials of degree n. And then the issue here ends up being, well, what are the interpolation points that I end up using? So what we do is these phi are going to get replaced with Lagrange interpolating polynomials. I'll say the ith Lagrange interpolating polynomial. So let me go through and replace those. Okay. And I'll just move that derivative up just to make that look a little bit nicer. Okay, and then on the right-hand side, I still have Li dc. Okay. And then this statement for all phi in the space of polynomials to degree n, what that becomes is for I equals 0, 1, 2, all the way up to n. So the 0 through nth Lagrange interpolating polynomial. That's what we're doing here. So this gives us a way to generate n equations for a single element. So the question might be, what the heck are the n unknowns here? Well, since we're using Lagrange interpolating polynomials, we can actually, since the solution is a polynomial degree n as well as the flux and the source term, we can approximate the solution as so it's a sum I equals 0 to n of the nodal values of the function at the interpolation points multiplied by those same Lagrange interpolating polynomials. And so the unknowns for our problem are these s sub I. That's what we get. So we have n unknowns per element by requiring that we solve this equation for all polynomials of degree n. In other words, for I equals 0 through n, if we use the Lagrange interpolating polynomials as a basis, we get our n equations out from that. Okay, so we're almost there in terms of defining this discretization. This is incredibly important to make sure we have, because without defining the discretization, I can't show you how to do mass and momentum conservation for the discrete system, which is something we want to make sure that if we start from the conservative form and we go through this process that we actually get basically a conservation law that's consistent with the continuous equations. Okay, so let's clean up a couple things here. So now we're at this point. We know that essentially we are replacing the solution with the what is this, a weighted sum of the Lagrange interpolating polynomials. The last thing to do is handle these integrals. Now these integrals, right now they're continuous. What we do to handle that part is to recognize, one, that if this is for polynomials, then this right here, whoops, not what I wanted, this is a polynomial of degree n, as is that, and so I have an integrand that's a polynomial of degree 2n, so we can use Gauss type quadrature, so this is either Gauss or Gauss-Lobato points, Gauss or Gauss-Lobato quadrature to evaluate these integrals. And so what this ends up looking like, so let's do this first one here. So we have the integral minus 1 to 1 ds dt L sub I of c dc. One, I'm going to go ahead and replace my solution with its interpolant. So I have the sum j equals 0 to n, s sub j, I'll just go ahead and do a dot over top to indicate a time derivative, Lj c, then I still have my test function out front, Lic dc. Okay. Now, when we do quadrature, that integral becomes a sum. So I'm going to do another index here for that summation. We have the sum k equals 0 to n. And then I have the sum j equals 0 to n from the interpolant for the solution. I have sj dot Lj. And now I'm evaluating the Lagrange interpolating polynomials, the integrand, at the quadrature points, the locations where we choose to evaluate these functions. And this is like I said before, either the Legendre-Gauss or Legendre-Gauss-Lobato. Of course, you can also use Chebyshev, Chebyshev-Gauss, Chebyshev-Gauss-Lobato, Lick. Now, if we make, all right, and we have the quadrature weights out front, okay. If we make the judicious choice that the interpolation points are exactly the same as the quadrature points, we can take advantage of a Kronecker delta property of the interpolating polynomials. So I get delta jk here, I get delta ik here, and so the mass matrix, if you've done finite element analysis, this matrix that we're forming from doing this problem this way, it's called the mass matrix. This mass matrix ends up being diagonal, which is incredibly efficient to work with, because inverting a diagonal, it can be reduced to just dividing by a scalar. Okay, so what this ends up reducing to is basically only the j equals k term survives on this one, and only the I equals k term survives from this one. So only I equals j equals k survives. And what I'm left with is just Si dot omega I for that mass matrix. Okay. So some notation I need to introduce you to, because basically, you know, if you go through this process for each of these terms here, so we did this first one, the last one here for the source term is almost the same thing, except we end up with qi here. That's no big deal. The term with the derivative in there is a little bit different, simply because the Lagrange interpolating polynomial derivative at those points does not have a Kronecker delta property. Instead, we get basically a matrix operation. So let's do that real quick, and then I just want to introduce some notation that I will probably be using today, so that it's not too confusing later on when I throw that in there. So let's do this other matrix. Let's do this term right here. So I've got, again, integral minus 1 to 1, the flux function, multiplied by L prime I of c dc. Okay, so again, I'm going to go ahead and replace the flux function with a nth degree polynomial. So I'm committing an error, yes. I'm committing an error because the flux function is usually a nonlinear function of the solution. And so I incur an aliasing error here, but that's okay. We're going to live with that. So I've got this, again, the sum j equals 0 to n. I've got f, j, Lj of xc, and then L prime I of xc dc. And again, we're going to go ahead and substitute in with our discrete quadrature. So I get the sum k equals 0 to n, sum j equals 0 to n, fj Lj ck L prime I ck, and again omega k out front for those quadrature weights. Now we get one of these sums go away because we have the Kronecker delta here, delta jk, so only j equals k survives, and what I'm left with is the sum k equals 0 to n. Okay, I get f, again j equals k survives, so I got f sub k, L prime I ck omega k. Okay, so I get a little bit of a derivative operation going on here. Now to explain to you why I'm going to write this as, if I were to write this in matrix form, what we write it as is a mass matrix times the derivative matrix transposed times the vector of the nodal values of the flux. The reason why I put this as a transpose is because, no, don't clear the frame, is because if I were to think about calculating a derivative in the strong form, so the strong form being if I were just to calculate df dc directly using that interpolant, so I got j equals 0 to n, fj Lj of c prime. If I were to evaluate that at each of the points at ci, that just becomes an ci inside of there. And what I have is a matrix, so for each I, so for row I, column j, if I basically do this kind of operations, this is where we would write this as a derivative matrix multiplied by a flux of those, a vector of those flux points. And so when we put it in the weak form, what it turns out what we end up getting is this mass matrix multiplied by the derivative transpose. So I'm introducing this because a couple points I might be switching between the matrix form and this sort of pointwise description of the weak form of the system that we're solving. The other way to look at this is what's called inner product form. And it's actually kind of helpful for doing some of the derivations that we'll be doing here shortly. But if I were to write this in inner product form, so one, we're going to define the inner product here. So if I have u, v, and if I put a subscript n, what I'm essentially indicating here with the subscript n is that I'm doing discrete quadrature. Okay, so u, v, n is just going to be sum k equals 0 to n, uk, vk, omega k. And then if I were to say u, v without the subscript n, it's going to be the integral minus 1 to 1 uv dc, so the continuous form. Now the cool thing is, as long as u and v are both polynomials, we can actually use properties of either. So like for example, if I prove a property for the continuous inner product and u and v are both polynomials of degree n, in other words the integrand is a polynomial of degree 2n, so long as I'm using Gauss type quadrature, I can assume that properties of the continuous inner product hold for properties of the discrete inner product. So we're going to take advantage of that to actually prove mass conservation pretty easily, because essentially if I can commute between those two, I'm good to go. So what the system ends up looking like in this inner product form is we have a delta xk on 2 out front. I have the inner product of S dot with the ith Lagrange interpolating polynomial with the subscript n out front. I've also got the inner product of F with L prime I sub n. And I'm going to go ahead and pull over the source term. I get delta x on 2. Inner product of Q with L sub I. Again, subscript n because I'm doing the discrete form. And on the right-hand side, what I've got is the evaluation of the negative evaluation of the difference in the Riemann solution weighted by each of the Lagrange interpolating polynomials. And again, this is for I equals 0 to n. So I've got really n equations, sorry, n plus 1 equations encapsulated here. Okay. So let's talk about a couple things here. One is if I'm doing volume conservation and momentum conservation, all I'm essentially doing is replacing the L sub I, okay, with a constant, with just 1. So I'm essentially, for example, if I were to look at what the inner product of S dot with 1 is in the continuous form, what that would be the integral over space, so minus 1 to 1, S dot dc. And this is the quantity we're after when we're looking at trying to prove mass or momentum conservation. So if I essentially go back into this form here, and if I were to replace each of the L sub I with 1, all right, L prime of I, which if I'm putting 1 in there, is actually 0. So this, so let's put that L prime back here. So if I'm looking, if L sub I is just 1, again, just trying to prove that mass and momentum conservation, this term right here goes to 0 because the derivative of 1 is 0. Okay. And then on the right-hand side, I get the average value of the source terms. And then over here, I get the fluxes at the boundaries. And again, because now I've got a polynomial of degree n inside of here, which is still exact. I've got a polynomial of degree n over here, which is also still exact. So I can actually rewrite this as, this is the equivalent of doing S dot 1 in the continuous form. And since in the continuous form we know the shallow water equations conserve mass and momentum, the discrete form certainly does. So that's actually pretty easy, and it's nice when we start with the conservative form of the equations and do the discretization from there. All this stuff drops out pretty naturally. The problem ends up being when we try to do entropy conservation. So William asks, is there a particular reason to use Lagrange interpolation as opposed to a cubic spline? The reason we choose the Lagrange interpolant, so there's actually a couple things that are going on underneath the hood here. Really where this comes from is, in the spectral methods community, what was done before was to do what are called modal approximations. So I'll kind of take a step back here. In modal approximations, if we're looking at all possible polynomials of degree n to approximate a function, what we would write is, for example, I equals 0 to n. I'll call these f hat k's, and we'll call this capital L, fi, capital Li of c. And the bases that folks try to choose, they usually try to choose bases that are orthogonal. And what I mean by orthogonal is they satisfy the property that the inner product of Li, Lj, which are two different functions in that bases, if I do the continuous integral, is going to have this Kronecker delta property. Okay. Now, the problem with working with this kind of form is what you end up with as your degrees of freedom are modal coefficients, so with an m. And to get back to basically placing things into physical space, you have to go back through and basically evaluate this modal expansion at a whole bunch of points. So it adds some computational complexity. So the way around this is to choose an interpolant. So we basically want to set a different expansion, I equals 0 to n, where we have modal coefficients using we use Lagrange interpolating polynomials because they give us the ability to work with nodal values at specific points. And it just so happens that if we choose the quadrature, so the way we do discrete integration, to preserve this property for the underlying modal polynomials that we wanted to work with, so this would be your Legendre or your Chebyshev functions, we can show that the error associated with doing this kind of interpolation, choosing the interpolation points to match those quadrature points, ends up incurring two errors. One's a projection error, which is basically an error that is, the projection operator is really the best possible solution you'll get by representing a function as a polynomial of degree n. And then you get an aliasing error, which is essentially, I mean, if you've done Fourier series, it's the same kind of aliasing error you would think of there. It's the error you incur in evaluating Li, Lj as a discrete inner product. But yeah, the reason why you end up sticking with Lagrange interpolating polynomials is really because they have this Kronecker delta property when you go through the derivation, so you get nice and easy to work with mass matrices that are diagonal. This definitely is a choice for computational efficiency. So we know, like, basically at this point, I'm hoping I've convinced you that by starting with the conservative form, it's very easy to come up with a statement that should convince us that, at least in the discrete form, we end up with conservation of our prognostic variables. Again, the problem ends up being when we want to do energy conservation. So let's talk about energy conservation. And in the literature on this topic in the spectral elements community, what they refer to is what they'll call entropy. It's mathematically, it's called an entropy function. But essentially, it comes down to just defining a single scalar function that depends on all your solution variables. That is, one, it's convex. And two, the entropy function ends up needing to satisfy this kind of statement. So if I have a conservation law that looks like this, I should be able to define an entropy function that depends on the prognostic variables that has a conservative flux. And additionally, if the functions are smooth, if the solution is smooth, this should be an equality. So we should be able to prove conservation of the entropy if the solutions are smooth. If there are shocks or discontinuities in your solution, we require that the solution really approaches what's called the vanishing viscosity solution, which it turns out to basically be something that decreases the entropy. In some sense, this does make sense, because, like, if you're doing compressible Euler equations or even shallow water equations, you're thinking about modeling things at a large scale where, for the most part, we've ignored viscosity or viscous effects in general. But I think, underneath the hood, we all know that at some point, viscous momentum fluxes are going to occur, or viscous mass fluxes are going to occur. And so, of course, underneath the hood somewhere at some scale that our hyperbolic system is not capturing, we know that there's some kind of dissipation that's there. And so when a shock develops, really what it means is, in our discrete problem, is it's approaching the limit at which we can resolve something happening. And in order to keep the model stable, we need to kind of provide some kind of dissipation to smooth that out. That's really what that statement is saying for us. So let's think for a minute, though, about 1D shallow water equations. Again, I'll put these guys back up here. I have h dh dt, hux is 0. I've got hut for the momentum equation. And I'm going to write it in a slightly different form because it's a little bit easier to work with when we're talking about entropy conservation. That pressure gradient term, I'm going to take that gh squared on 2 outside of that first term we had there, and just pull it out front. So we get h minus hx. And for those of you who have done oceanography, physical oceanography before, or you're familiar with shallow water, this h minus h is really just the free surface height. And that's the thing that controls the barotropic pressure in a constant density, thin fluid. What we mean, again, although I'm saying entropy, I'm not talking about like thermodynamic entropy. What I'm really referring to, again, is just a function that combines the solutions in a very particular way to get us this kind of statement. And it also helps if that entropy function is what we call convex. In other words, its second derivative, if you're dealing with a single variable function, is always positive. What it means for multivariable or multiple equations in a PDE, or multiple prognostic variables, is that the Hessian matrix is positive, so its eigenvalues are positive. For shallow water, what the entropy function really is just the total energy. It's the sum of potential and kinetic energy. And so what I'm going to do here is just show you briefly how we come up with what we call the entropy for shallow water, in other words, the total energy. And it's actually, there's a couple steps that we can do to make this derivation really easy and painless. So one, we're going to work with this form of the momentum equation, because this is the term that really causes a lot of problems for us. And then we're also going to look at the advective form. And the advective form is essentially, if you remember a couple weeks ago, when we were looking at different ways to define the conservation laws, what we can do is, instead of writing this as a divergence of a flux, the advective form essentially writes this as the Jacobian matrix, so the derivative of the flux with respect to the prognostic variables, with the matrix vector product with the gradient of, not the flux, gradient of the solution variables. And so this is really the advective form, and you'll see in a minute why this is actually quite nice to work with. It makes at least deriving the kinetic energy conservation very, very simple. So we're going to do this. We're going to look at creating the advective form for the momentum equation, and then looking at the average of the advective form with the conservative form actually gives us what's called skew symmetric, and you'll see a lot of stuff just drop out real nice when we go through and essentially multiply by the velocity field to get us the kinetic energy. Okay, so the advective form, essentially what we can do starting from this conservative form here is apply volume conservation and rewrite this whole statement as h multiplied by du dt, this the velocity, plus h u du dx plus gh dh dx. H minus h, big H minus little h, so the free surface height is 0. Pretty straightforward, and the reason why we can get away with pulling that h out and then canceling other terms is, again, because the other equation here that we have enforces volume conservation, allows us to basically get rid of the other term that comes out from backing ourselves out of a product rule. Now, if I were to look at the skew symmetric form, essentially what I'm doing is averaging this equation with that equation. So what I end up with in the skew symmetric form is 1/2 total derivative HUT plus HUT with h outside of the time derivative here. And then I have for my advective fluxes, I have HU squared x, and then I have HU ux inside. And then if I, of course, I average the same term together, what I'm left with here is GH, H minus H, X is 0. Now, to get an equation for the kinetic energy, essentially what I want to do is multiply this whole equation by U. And if we think about, just keep in mind when we're doing this sort of like inner product notation, what I'm going to end up doing later when we go do the discrete conservation is I'm going to essentially be replacing L sub I with the solution itself to basically back out an energy here. So we're basically doing the same thing in the continuous form, and we want to make sure that when we go through the discrete form, a lot of these steps that we're taking are actually going to be preserved when we go to the discrete form. Okay, so if I multiply by U inside of here, I get 1/2 U HUT plus UHUT. I know if I'm just saying it, it sounds like I'm saying the same damn thing. However, if you're following along here, there's some subtle things that are happening inside. We have 1/2, again, for those vector terms, we have U HU squared dx plus HU ux. Whoops, I'm missing a U there. Let's fix that. I'm actually going to write this as HU squared ux. Okay. And then again on this last term here, which is pretty easy to work with, we got GHU, H minus H, X derivative. Set that all equal to 0. So this first term, again, since we're working with the continuous form, we can use a lot of rules right out of the box. Like product rule or chain rule, things like that. So we're going to go ahead and take advantage of that here. Now, unfortunately, when we go to doing this with interpolants, product rule and other rules like that actually break down, and there's an error associated with that. But we'll show a way to overcome that. So this first set of terms here, if I were to pull that u inside, I get hu squared on 2. If I pull the u inside there, the hu inside of there, I get hu squared on 2. So what I'm left with is hu squared on 2 from that 1/2 out front, dt, plus 1/2 u hu squared x plus hu squared ux plus, I'm just going to put quotes here because I'm just going to carry down those next few terms. Now, we can do product rule inside this second term, and what we'll end up getting here is I can do, let's see here, so I've got, what I've actually got is hu squared dx multiplied by u. I've got hu squared multiplied by du dx. So I can basically lump all that together. And I have 1/2 hu cubed x. Plus, I'm going to go ahead and carry down that term from the pressure gradient. Okay, so that's our kinetic energy balance. That's it. All it took was multiplying the skew symmetric form by u and basically applying a product rule for this second term. Now, in a lot of the derivations where we talk about stability, we're going to talk about the semi-discrete form, so where we're only discretizing space, and we're going to assume that there's continuity in time. This is very similar to, actually, this is exactly what was done in a paper by Gregor Gassner and Andrew Winters, David Kopriva in 2015. It's very astounding how all this stuff ends up working out when you do this in the discrete form. But this is our kinetic energy equation. So I'm going to go ahead and kill some stuff here because now we're going to do the potential energy. And the potential energy is going to be formed by doing an appropriate multiplication by the continuity equation by this guy up here to get out something that tells us a little bit more about the potential energy. So if I multiply the continuity equation by g eta, this is a free surface height. So in other words, h minus h. I got ht for that first term, and I've got g h minus h hux for that second term. This first term, again, assuming continuity in time, what I end up with is gh squared on 2 minus big H little h, times g t. This is our potential energy. So I'm just going to call that P. I'm going to go ahead and carry this guy down. Okay, carry it down one more step. Okay, so now if I go ahead and call hu squared on 2 our kinetic energy, and I've got our potential energy there, if I add those two equations together, what I get is total energy, right? Kinetic and potential. That total energy ends up being our entropy function, and I'll show you why we can say that, because essentially a few things are going to drop out here that are going to allow us to define a conservative entropy flux. So if I add together kinetic plus potential, what I end up with, so I'm going to add this guy, I'm going to add this guy. We've got K plus P dt. I've got plus the 1/2, let me go ahead and just move that inside. I've got hu cubed on 2 dx. And now if I were to look at this term here and this term here, one coming from the kinetic energy equation, one come from the potential energy equation, I've got g free surface height multiplied by volume flux gradient. I've got volume g times the volume flux gradient multiplied by the free surface height gradient. So I've got a product rule that I can apply between these two. Whoops, get the pen back. And so what I've got left here is g h minus h u h dx, all equal to 0, running out of space there. So if I were to combine all this together, K plus P is the total energy, and then I've got h u cubed on 2 plus g h minus h hu dx equals 0. So if I were to compare this with what's inside the integrand for that entropy condition, this total energy would be my entropy function, And then this HU cubed on 2 plus GH minus HHU, I know it's a mouthful, would be this entropy flux function. So I have, with the shallow water equations, a way to define a conservative entropy flux. Now, if I were to think about doing an integral over all space and time, assuming my solution is absolutely continuous and I can take derivatives of it, if I integrate over all space and time, so we're going to be integrating over x here. What I have on the first term is ET plus, and then I have the entropy flux, which let's go ahead and just put that as entropy flux dx. Okay, if I do the spatial derivatives, if I do the spatial term using basically rules of integration, what I can show is that the entropy at the later time t, integrated over all of space, is less than or equal to entropy integrated over all of space from the initial condition minus any entropy that comes in from the boundaries over time. So I get psi at the, if I put my boundaries at -1 and 1, this is what I end up with. And if I have, for example, for the shallow water equations, the entropy depends on the velocity, for example. So if I had no normal flow boundary conditions, for example, the entropy flux from the boundaries would be 0, and I can bound my entropy at a later time by the entropy at the initial time. And like I said before, if the functions are smooth and continuous and I can take derivatives of them, what I actually get here is equality. So I should be able to ensure that the entropy later does not change. And that kind of makes sense if you think about shallow water equations. All we get from shallow water equations are gravity waves. They move energy around, but they don't change the total energy of a problem. They just migrate it from place to place. So that's essentially what that entropy condition does for us. And that's in a continuous form. So at this point, we should be convinced that the shallow water equations do have an entropy function, and that entropy function is conservative. And this is what we want. Remember, if I go back to our motivation here, when I said I want a stable method, if I want my method to be stable, this is where I'm pulling that criteria. I want to make sure that the discrete form of the system I'm solving has this property. We know that if we start from the conservative form, we got this one for free, and this last one here is actually quite subtle, so we'll discuss that in a little bit. Okay, so that is entropy conservation. So let's talk about what goes wrong when we try to get entropy conservation starting from the conservative form. So again, we've got our conservative form, HU of x equals 0. HU of t, and again I got HU squared plus GH squared on 2 of x equals GH HX. Okay, so let's just look at the kinetic energy, or sorry, the momentum equation, and we'll form a kinetic energy equation. And going forward, just keep a couple things in mind. I'm only doing this just to make notation a little bit easier. HU is a polynomial of degree n. So we've replaced it with its interpolant at this point. This term, the flux, we've also committed an aliasing error, but this whole flux term is a polynomial of degree n. So HU squared plus GH squared on 2 has been approximated by a polynomial of degree n. So we've already committed this sin. There's one fact I do want to point out to you. If I have two functions, f, which is a polynomial of degree n, g is a polynomial of degree n, then f times g, really what it is, it's a polynomial of degree 2n. So it's in that space. Okay, but what this means is that if I approximate the interpolant f times g as an interpolant of degree n, what I really get is the interpolant of degree 2n plus an error. Okay? So this error I'll just call epsilon. So if I were to take a derivative on the left-hand side of the interpolant, Okay, I get the derivative of the actual thing it's supposed to be, the 2n interpolant. So the 2n interpolant has no errors, it's exact. But then I also get the derivative of the error I've incurred by approximating a 2n degree polynomial with an nth degree polynomial. And what this really means is that interpolation and differentiation don't commute. The derivative of the interpolant is not the same thing as the interpolant of the derivative. Now there's some pretty cool stuff you could do here to prove some properties about this particular error that's actually going to help us in a little bit here. So let's prove a couple properties about how that error behaves, and kind of go from there. So what I'm going to do is define, so this guy here, the derivative of that interpolation error, let's just call it delta. Okay, and let's write out what each of these interpolants are. So if I do the interpolant of f times g, what I get is the sum j equals 0 to n, fj, gj, lj of c. And this guy is an nth degree polynomial, so I'm going to put an n up there, not putting it to a power of n, I'm just using that as notation to indicate that this is the nth degree Lagrange interpolating polynomials. Now the 2n degree interpolant of fg would be some, let's use a different index here to not confuse things, k equals 0 to n, fk, gk, and this is now using the 2n degree polynomial, lk of c. All right, so if I take the difference of these, I can get this delta function, this error that I'm looking for. Okay, so from here I get the error in that interpolation that I've made is just going to be, oops, I'm missing, that's a 2n up there. I get sum k equals 0 to 2n, fk, gk, lk 2n of c minus sum j equals 0 to n, fj, gj, lj of c. Okay. And if I were to, sorry, that's going to be epsilon there, as I haven't taken the derivative yet, my bad. Okay, so if I take the derivative of this, I get delta that I'm looking for. So delta, and so what I'm really trying to quantify here is an error in the lack of conservation of a product rule. Because differentiation and interpolation don't commute, product rule doesn't hold. And so we want to kind of understand this product rule error because it turned out product rule was pretty important for this energetics proof that we had. All right, so anywho, the delta we get is sum k equals 0 to 2n, fk, gk, lk, 2n, and we're going to take a derivative, so prime, minus sum j equals 0 to n, fj, gj, lj, n prime. Now, let's go back just one step here to motivate what I'm going to do next. When we looked at entropy conservation, not only did we come up with a point-wise statement for that entropy conservation, we took an integral of that entropy, because really what we care about for stability is if the integral of the entropy that we're looking at is conserved, right? So, again, in the process, what it ends up meaning is I have to take an integral of an entropy flux, and that entropy flux, to get to that entropy flux function, I had to use product rule. It would make sense to try to understand what the mean value of this error is. So in other words, when I look at the error in approximating a interpolant of two polynomials, so a polynomial degree 2n with a polynomial degree n, what I really care about to make sure I can have entropy conservation is if the mean value of this product rule error goes to 0. That's what we would want in order to be able to at least say that the mean entropy, the total entropy, is going to be conserved. So the way we do that, right, is of course if I look at the integral, let me actually clear some space and do this higher up here. If I take an integral of this error function that I've got, So let's say I do it on -1 to 1, just because we're doing this on our reference elements. The integral of delta is going to be the sum k equals 0 to 2n fk gk. I've got an integral of a derivative, so what I get is the 2nth degree Lagrange polynomials evaluated at the endpoints, minus the sum j equals 0 to n fj gj, and now the nth degree Lagrange interpolating polynomials evaluated at the endpoints. And this is where the choice in quadrature actually matters. This is something I learned in the last couple of weeks that I found pretty spectacular, and it's changed my opinion on Gauss-Lobato points. So the deal is Gauss points, when you do your Gauss, so let's talk about this real quick. So the Gauss points on -1 to 1 are interior to the domain, -1 to 1. They don't lie on the endpoints. They don't include -1 and 1. So if I want to calculate the Lagrange interpolating polynomials at the boundaries, I really got to do an interpolant to prolong the functions to the boundaries. And now if I do that prolongation for a polynomial degree of 2n, and using that expansion, I get a number for f times g. And if I do the prolongation using an nth degree polynomial, I get a different number. And so these terms don't actually cancel out. Okay? What ends up happening though, for the Gauss points, the Gauss-Lobato points have, so for this guy, L2n k of 1, it's going to have a Kronecker delta property with the endpoint. So it'll be 2n k, 2n comma k. For the left endpoint, we get 2n minus 1 is going to be Kronecker delta 0 in k. Now, for the Gauss-Lobato points for the other one, I have Lagrange interpolating polynomial degree n. Lj of 1 is going to be Kronecker delta n, nj. And then we get, for the other point here, at -1, we get Kronecker delta 0 comma j. And because I end up having these points on the boundaries, what I actually get are the nodal values of the function at the endpoints where we've already co-located errors. And so it turns out if I use a 2n degree polynomial and an nth degree polynomial, I can actually, as long as I'm using Gauss-Lobato points, show that this is identically 0. So although the product rule from point to point still incurs an error, when you use Gauss-Lobato points, turns out the mean value is 0. So that's actually really helpful, because what we can do from here is actually do a discretization using the skew symmetric form, which is what was done in this paper from Gregor Gassner, Andrew Winters, and David Kopriva. They start from that skew symmetric form, and essentially what you arrive at when you do this derivation starting from skew symmetric form is you get the conservative form. So what they're calling U1 here, let me get that to go away. U1 is the total fluid thickness, so eta minus h, or basically the water column height. We have a conservative derivative of the volume flux, and then you end up with boundary terms coming from those Riemann solvers. For the momentum equation, you can actually, it turns out that the skew symmetric form when you discretize ends up being exactly the conservative form, plus these additional product rule errors for the momentum flux and the volume flux on the right-hand side. And so although point to point you introduce an additional error, when you integrate this over over the elements, the average values of those additional terms go to 0, much in the same way I just showed you they would before, so long as we do this discretization using the Gauss-Lobato points. Now there's a couple other bits that go into making sure we have entropy conservation, so where we have that total integral of the entropy equation less than or equal to 0, and it comes down to how we choose the Riemann solver between neighboring elements. It turns out to be incredibly important. And this is a lot of material to try to cover in a whiteboarding session. So what I would like to just suggest is that if you're interested in this material, is to check out this paper from Gregor Gassner, Andrew Winters, and David Kopriva, where they kind of walk through a lot of this material. But essentially what it comes down to is exactly that. You start from the skew symmetric form, you use Gauss-Lobato points, and it's the discrete system you end up coming up with is the conservative system that we already had before, so we can easily modify an existing code by adding these additional terms out in front. And those additional terms defined below is just 1/2, so we have the derivative of hv squared, so the momentum flux, we have the difference between that and then the actual product rule form. If you were to expand that in a product rule in the discrete system, that right there is the product rule error. Same thing here for h squared. If we expand out doing a product rule for h derivative of h squared, we can calculate the error from that term and basically drop it right back into the conservative form equations that we had before, and it does not mess with mass and momentum conservation, because again, if I integrate this over an element, the average value goes to 0, so I still get mass and momentum conservation even though I started with skew symmetric. And then you also get entropy conservation out of it so long as you choose the flux functions in a very particular way. So that's pretty much it on the theory. There was a whole bunch of reading that went into this over the last couple weeks. Let me actually move this over so you can take a look at some of those references there. Particularly this paper from Gregor Gassner. I'm not sure what happened to the... that's really weird. Particularly this paper from Gregor Gassner in 2015 is the one that a lot of this material was based on today. And where this is going, so from this 2015 paper, there was a couple bits of follow-up between folks who work together in this community, particularly Hendrik Renosha and Nicholas Wintermeyer, 2016-2017, where they expanded that same kind of methodology to 2D systems. The problem with 2D when you start to have isoparametric elements is you also have metric terms to worry about, which is what we'll be talking about in 2 weeks. Particularly, it's not just enough to have Gauss-Lobato points, and basically starting from a skew symmetric form. Well, one, skew symmetric form in 2D is a bit more complicated, and you end up having to relate basically gradient curl and derivative divergence operators through various product rules in vector calculus to be satisfied. So it gets a bit more intense there, and then of course, like I said, metric identities end up playing a role in that, which we'll talk about in 2 weeks. So all I'm going to do from here is we're going to transition over. I want to show you just 2 scenarios. So one we had done 2 weeks ago where we just did the quiet fluid with a flat bottom for the conservative form equation. So surprise, surprise, that case is actually not too hard. We can maintain a quiet fluid. And then I'll show you an example where we did a basically a quiet fluid with a hill in the center. And show you that we actually are not able to maintain a quiet fluid. So we'll do that, and then we'll take a look at putting together, basically wrapping up a conservative form for the 1D shallow water system and doing some of the GPU programming required to get that off the ground, so that those of you who are interested in the GPU programming side of this can see how that's done. And we'll kind of basically from here until the next time, we'll be putting in some of these additional terms to stabilize our system. So let me go ahead and change over here. Okay, so the first thing I'm going to show you is, let me just go ahead and hop into the source code here, make that a little bit bigger. So what we have, if you remember from last time, we put in this shallow water solver, the nonlinear shallow water solver in 2D, which was, if you've been following along, we've been basically building up some objects in Fortran for us to basically kind of reuse a lot of code underneath the hood, so we don't have to define a bunch of time integrators every time we want to do a new model. But we extended this generic model 2D setup to define shallow water. And right, so we just basically did the conservative form of the shallow water equations here. So we defined the flux method. So let's look at flux shallow water. And these are on the GPU. I'm actually currently experiencing some correctness issues with the GPU methods at the moment, so I'm in the midst of debugging that. But if you follow us on Open Collective, and if you end up becoming a member of the higher order methods community, you'll be able to see updates about that as those issues get resolved. But essentially, right, so we have for the U equation, we did HU squared plus the pressure gradient. We've got the advective fluxes from the V direction, right? And then, yeah, everything else from here. So essentially we have a shallow water equation solved, and we set up this example to do a quiet fluid. I think when we left off last time, I was encountering a few issues that we have since resolved on the CPU side, which is great. Let's take a look at that block mesh 2D quiet fluid. Okay. So for those of you who are new to working with self, essentially writing a program comes down to just defining a few things. One, we need to have a domain decomposition object. So this allows you to take advantage of all the MPI features underneath the hood, so you can do cluster computing. And if you have GPUs, this allows you to also do multi-GPU computing. We're going to create an interpolant. Now the interpolant we're using right now is a degree n, which is degree 7, polynomial with Gauss type quadrature. So this uses the Legendre Gauss. As I pointed out earlier, we need to end up changing this to Gauss-Lobato. I will say Hendrik Renosha in his paper has some proofs that show you can actually get entropy conservation with Gauss points, but it's a little bit more complicated to implement. So we'll probably end up just switching to the Gauss-Lobato points here in a little bit. So yeah, we create an interpolant which interpolates from the Gauss 7th degree Gauss quadrature points to a 15th degree uniform grid, which allows us to do plotting on a nice uniform grid. We talked about last week how to do mesh generation with Hoke mesh and Hopper. So we're reading in a Hopper mesh at this point for the 2D and 3D problems. Really, we're basically relying on Hopper input files for that. Generate a domain decomposition. If you did want to set all the boundary conditions to a single type, we have built-in methods for that kind of stuff too, which is kind of nice. And then we generate metric terms. So if you remember what we're doing, right, is each element, just like I did in 1D, we map to a computational space. In 2D and in 3D, we will take each four-sided quadrilateral, even if it has curvy sides, and map it to a reference element with straight sides, -1 to 1 in each direction. So basically, once the mesh is generated and we have an interpolant, we can go through and define that mapping and create the metric terms that we need to calculate divergence, gradient, curl, what have you, in 2D. So we can initialize from here the model that we're working with. So a model, really what it needs is a mesh. It needs geometry and it needs a domain decomposition. So that's what we do there. We have a simple call just to enable GPU acceleration. Underneath the hood, this checks to make sure that you have a GPU. And if you do, it will actually make sure that it's doing the appropriate data copies between the GPU and CPU when it needs to ensure correctness. And it'll also launch kernels underneath the hood that have GPU kernels associated with them. It'll launch those on the GPU, so you could take advantage of GPU acceleration pretty easily. Right, so in this case, what we did is we set the topography just to be at a constant depth of 1, so there's no variation. And then we had the initial condition that total fluid height is also 1, so there's no variations in the free surface height. Completely quiet fluid. So we'll write out those initial conditions. I'm going to use the RK3 time integrator, and we'll forward step. I think this one's just configured to do a single step to make sure that things stay quiet. Because if it can't stay quiet for a single step, it's certainly not going to do it for 100. And then the last bits here, we have some error checking in these examples because they're part of the continuous integration process. Now, the other test case we've set up is basically the exact same thing, except now we have topography. So the topography is really just going to be given by a little hill that has a height of 0.2, so it's a Gaussian hill. And then the total fluid height is going to be set to the same thing. So again, the free surface height is fixed. Okay, so over here I'm actually in a Docker container at the moment that I've built previously. And what we have going on at the moment is, so here's that shallow water quiet fluid block mesh 2D benchmark. So this is the one with the flat bottom. The initial entropy, when you calculate that entropy using the function we defined before, you get minus 0.5. And then later we get minus 0.5. So nothing moved. So that's pretty good. And I'll actually show you, we'll go ahead and run that example now. Let's do shallow water, quiet fluid, block mesh 2D. Okay, convince you we've got new output here. That time's looking right for me over in the mountains. And we've got our new tech plot files. So let's open up ParaView, which I have open in another window. We'll reload this guy. And what we're looking at right now is that total fluid thickness, which if it's red, it's set to 1. And if I toggle back between the initial condition, which is what we're looking at right now, and the solution later, nothing's changed. I can also look at U and V. Again, nothing. So we've stayed quiet for the flat bottom, so at least we can claim victory there. Let's take a look at what happens when we add topography. All right. So the example program picked up on the fact that the entropy changed, which that's weird. It's not printing the correct value there. Figure that out. But it also picked up on the fact that the velocity field is now non-zero. So the free surface height looked like it stayed mainly the same, but now we've got some non-zero velocity here. So let's take a look at what that looks like. So after running that, I do have a new tech plot file. So I got new output. And let's reload this. Okay. And so this is looking at that second time step, and I've got a little bit of motion generated, and the velocity field is really associated with where the boundaries of the elements are. So if I put those edges back on, you can kind of see that those line up with where the element boundaries are. So I know I'm doing this in 2D, and all the stuff we proved earlier is in 1D. So I went through and I wrote a 1D shallow water solver. And this is where we're going to pick up today because I haven't quite finished that one. We're going to go ahead and do the GPU implementation for that, for those of you who are interested in seeing how that gets done. And we'll go from there. So what we have that was recently added was this shallow water 1D. And much like the 2D one, here we're doing a type extension of the model 1D class. We actually don't need a Coriolis force in the 1D model because there's not two components of the velocity anymore, so we'll go ahead and get rid of that Coriolis force, or the Coriolis parameter. So what we've done, much like the 2Ds, basically so far what I've done is adapted the 2D solver. I've copied that over to this 1D file. So we have overrides for the initialization so that we can define bottom topography and the bottom topography gradient. We have a method for calculating entropy, which is the same one we had before. So I'll show you what that looks like. Okay. So it basically loops over the grid, and we pull out HU, so the volume flux. We pull out the volume, the fluid thickness H, and then the bottom topography, and calculate HU in parentheses squared divided by H to get us H little u squared. And then we have the potential energy down here, right? And then to do, of course, to do that integration over all the space, we multiply by the Jacobian and then the quadrature weights. That's really all that's going on for the entropy calculation. So if you were to build your own model, this is actually, since we last met 2 weeks ago, the entropy calculation is a procedure you can override. And this is actually quite helpful for, when you're building models to be able to track stability, to help verify that you're implementing something correct. So if you want to see what ends up happening with that, when you do let's see, I think it's the forward step methods. When you do the forward stepping, automatically the forward step methods will automatically run through that entropy calculation at the end of each I/O interval that you have and report that entropy to screen. So when you call any of the integrators inside self, what it's going to do is it's actually going to run the integrator that you chose. So here we're looking at Euler. If you did RK3, right, it's going to forward step with RK3. It's going to, if you ask it to write out the model output, it's going to write the model output. It's going to write tech plot. It'll calculate entropy for you, and it'll report it to screen. And that's what you saw when we ran the container earlier. These outputs here, it's going to report the time and the entropy. The next things we're putting in are just prognostic variable integrations over there, so you'll be able to track mass and momentum conservation, for example, automatically. Now, if you don't define a entropy routine, the default that gets executed is just to fill in the entropy as 0. So it'll still run, but it just won't be anything meaningful for you. So again, if you're defining your own model, much like I'm doing here, you can provide your own method for calculating entropy should you want to track that over time. As before, we do have a pre-tendency calculation to calculate the velocity from the volume flux and the fluid thickness. And then as we've had for a while now, the source method, flux method, Riemann solver, and then a method for setting your boundary conditions. Again, if you don't set any of these, it's going to default to essentially doing nothing, so nothing will break. But certainly getting these defined is absolutely critical for defining your model. We did add new methods to this type extension to be able to set the topography. And the reason why we needed to do that is because in this type extension, topography itself is something that's not included with Model 1D. So this is a really good example of how to do that type extension in Fortran to really concretize a specific conservation law solver you want to solve based off of what's available in that existing model. Now, in terms of how things get forward stepped in time, there's a method, and I'll show you the one in 1D since we're doing 1D stuff today. This workflow you get for free if you do a type extension of any of these model classes. So you don't have to worry about making sure that you're making the right steps to do the forward integration. So long as you define source method, Riemann solver, and flux method correctly, you get to take advantage of things like side exchange, which is the thing that handles all the MPI stuff under the hood, so you don't have to worry about programming MPI stuff. You just have to think about filling in your source, Riemann solver, and flux method to solve your problem. Like I said already, if you know how to calculate the entropy for your system, it's also a free way to keep track of the stability of your model, and you don't have to worry about putting in all that extra engineering to make that happen. You also take advantage of flux divergence routines that are reused for every single model to do weak form derivatives. So again, you don't have to program it up. Now, of course, when we go to implement the correction terms for the shallow water equations, we're going to have to actually override that flux divergence method. But that's actually not too bad to do because what it does underneath the hood is just use the Lagrange interpolating polynomial class to compute a derivative or a divergence in the weak form. And because Gassner and friends proved that all we have to do is add a couple correction terms, we can just copy this method, add in a do loop underneath to go over all the elements and add in those correction terms. So it's really not too bad to make those adjustments to get things to where they're going to be entropy stable. And so, right, what we still need to do in this shallow water 1D is put in those GPU functions. And the way that's done, let's go ahead and take a look at doing the source terms. What we have for the source, yeah, shallow water 1D. So on the CPU side, it's just a doubly nested do loop in 1D. So probably not get a whole lot of speed up on the GPU for doing a problem this small, but I think just to illustrate how this happens, what we want to do is take advantage of, there's a parameter underneath the Model 1D class, the Model 2D class as well, called GPU Excel. It's that flag that gets set when someone calls enable GPU Excel. So what we essentially want to be able to do is call, and let me see what I called it up top. So what we want to be able to do is call this interface function. Whoops. There we go. We want to call that guy. And I'll show you how to define this function here in a minute if we're GPU accelerated. Otherwise, we'll go ahead and execute this loop on the CPU side. Okay, so that's what we want to have happen. So let's talk about how to get this function available. And of course, we'll have to fill in what source and solution are. You know what? Might as well do that now. So we got this. Underneath the model class, you have a lot of different variables available to you. So let's take a look at Model 1D. So you have a solution. There's a data type available for carrying the solution gradient. We have the velocity, flux, source, which is what we're going to use here. Flux, divergence, DSDT. This is just a work array. So if in case you're curious, each of these like these mapped scalar 1D types, what they are classes that house data that's interior to elements, data on the boundaries of elements, and for each of those, it hosts those on the CPU and the GPU. And there are methods underneath the hood to be able to transfer data back and forth, so you don't really have to think about a lot of that stuff. It's really handled deeper down inside of self. Of course, they have interpolants that are associated with them. Anyways, so what we want to do for the source is we want to work with the interior, so the element interior values, like you can see we're doing here below. And down below, we're working with host data. When we call the GPU, what we want to actually send is device data. So these are, in self, these are C pointers that are brought in from ISO C binding. And they're essentially what allow us to put the glue together with HipFort to get data onto the GPU and then to work with that on the GPU side. So we want the solution, again, interior device data. Okay. We actually don't need this Coriolis parameter anymore, so I'm going to go ahead and actually remove that from the interface definition. What we need is the degree of the polynomial, so that would be source interp, so the interpolant associated with that source term of degree n. We need the number of variables, so that's just going to be solution %n var. And then we just need the number of elements. Okay, so that's what we'll have there. Let me go back up and so what's going to happen next is what we need to do. So in self, the way I've organized this is underneath the source directory, there's a directory called hip, which is where we're going to put essentially C++ code that defines hip kernels that allow us to run on both AMD and NVIDIA GPUs. And I like starting from things that are already in the code because for the most part those work, and then we just modify those to suit the particular model we're working with. So I'm going to do, just to keep naming convention consistent here, so like you'll see I've got like self linear shallow water.f90, I've got a linear shallow water.cpp, there's a shallow water.cpp, there's a shallow water.f90. We're going to do the same thing with shallow water 1D. So we're going to copy the shallow water and do shallow water 1D.cpp. So let's open that up, and we're just going to go through these one by one and modify them. But to give you an idea of how these work, so one, let me go ahead and comment out things that I'm not going to define quite yet so we can kind of test as we go. Whoops, that is not what I wanted. Actually, this is C, so I can do this. I do like this about C, is doing these block comments like that. Don't have that in Fortran, but that's okay. And then we'll comment out everything else below for now, because we're just going to focus on the source term. And we'll bring those back one by one to get that going. Okay, so there's two C++ kernels we need to define. One is what we call the GPU wrapper. All this GPU wrapper does is serve as the interface to Fortran, and then it launches that kernel using the chevron syntax, which if you've done CUDA programming before, this will be familiar. But when you launch things on a GPU, essentially what you have, one, there's thousands of threads, but these threads are grouped together in what are called blocks, and those blocks are organized into what's called a grid. And the block size, typically the total number of threads per block is 2048 or less. But you can divvy this up into conveniently 3 dimensions. So like if I'm doing 2D operations, it's kind of nice because especially with the spectral element methods, I can think of my elements actually as being those blocks on the GPU, and basically each thread within that block is being, each nodal point within that element is being handled by a thread in that block. So that's all this launch syntax is here. So I actually end up using the polynomial degree for determining the number of threads per block, and then the number of blocks actually just loops over the number of variables and the number of elements that I have. Okay, so what we need here, so one, we're going to get rid of this Coriolis force, but actually what we need is, I think, let's pull up let's split it this way. Let's pull up the Fortran code. Okay. So what I need in the C++ code is I need gravity, the gravitational coefficient. So that's just a scalar. What I also need is a pointer to the topographic gradient. So that's grad h. And I've got the solution and I've got source. So that should be okay. So we'll go back and modify that call that we put in before on the Fortran side. And when I pass that down through to the GPU kernel, what I just need is the pointer, not the pointer to the pointer. So we'll do grad h, and then this guy we'll call g. Okay, so when I go up here, I'll make sure I have the same thing. I've got pointer, grad h, and then real, g. All right. So what I have for the first variable, so this is the fluid thickness in 1D, I've got g times the fluid thickness multiplied by the gradient in the bottom topography. Okay, so that's what we'll do here. I've got g times the fluid thickness, so that'll be solution. I've provided through a header file these macros, this SC, 2D index, etc. They're just macros that allow you to do multi-dimensional array addressing without using any special data types in C. I'm a fairly sticks and stones C programmer, so underneath the hood, all my C arrays or my C pointers are just flat 1D arrays, and they follow the memory ordering that we have in Fortran. And these macros allow you to use Fortran-like addressing to pull out what you need. And actually what I need is a scalar 1D index because we're doing 1D operations. So I'll get rid of that. Let's go ahead and do SC 1D index. We'll do over I. I don't need J anymore. I var, IL, N, and 1. Is that right? No, that should be n var. Okay, that might be my problem on the on the 2D GPU side. So it's kind of nice to be able to go back through this. So go ahead and get rid of this j again. Yeah, so the arguments here are the actual indices, so I var, il. So indexing over il goes over the elements, I var goes over the variables, and then we have the loop over the quadrature points inside of each element as that first index. To help with the calculation of those memory points, you need to know how many quadrature points there are, so we'll pass in n, and then how many variables there are, so that's n bar. Okay, so we've got g times h, which is, so we're doing zero-based indexing on the C++ side. So we need I var of 1 to get us the fluid thickness, il, and n var. And then what we need is grad h. So we have grad h, I, and here, looking up at the top, I've got grad h. I'm taking the interior point. I've got I var is set to 1 for grad h because I only got one variable stored for grad h. So on the C++ side, we set that to 0. And again, il, and the number of variables here for the topographic gradient is just 1. So let's do this proper and enclose that with a SC1D index macro. Okay, so I've got g times h times the solution gradient. Let's close that statement. And then for the fluid thickness, I've got no source terms, so I'll set that to 0. So that should be okay. Let's close this guy. Let's double check our work here. So I've got g times the solution, the fluid thickness here, times grad h. I think this looks good. And down below, we're launching with n plus 1. Yep, that looks good. That looks good. So let's steal that line. Let's go back into shallow water 1D. Whoops. All right. So what did that API look like? So we had source, solution. We need grad h down below. So let's go ahead and add that. Whoops. Then we need g, so the gravitational acceleration coefficient. And in order to make this a subroutine that we can call on the Fortran side, technically, I'm almost there. It's a little tricky if you were to do this without ISOC binding. You have to be very careful. But essentially, the object in the .o file that's created when you compile this with like hipcc -c and you create an object file from it, when we enclose a kernel with this extern C, what it instructs the compiler to do is to preserve this name, so source shallow water GPU wrapper, in the object file so that like I could reference it in other code. The caveat here is that it's going to append a underscore at the end of that object name. Okay, so if I were to go into Fortran side and just call source shallow water GPU wrapper underscore, I could be done. I prefer to be a bit more redundant, and I don't mind having a little extra code if it helps me understand what's going on. So what we actually do is we use a Fortran interface with ISOC binding to make this explicit, that we're going to have a subroutine called source shallow water 1D GPU wrapper that's going to basically point us back to that particular function. And that's what we were looking at up top before in these interface blocks. So I'm going to go ahead and paste this guy here just so we have that for reference. But we open up an interface block, we define a subroutine that has the same API. So I've got source, solution, grad h, and g, n var, and l. Here I've got source, solution, I need to add grad h, and I'll change that F to a G. So there's a couple things we bring in when you're inside these interface blocks. If there are other bits of other modules that you need to actually declare the use statements. Now keep in mind right here, you see we have the subroutine declared. We also have this bind specification. This is a line continuation here. So this is all like as if it were one line. We're going to bind this subroutine to a C kernel with the name source shallow water 1D GPU wrapper. So this makes it very explicit what this subroutine call on the Fortran side is actually going to do under the hood. So again, I prefer the redundancy because it makes it very explicit to anyone reading this code what's going on. Now, when you use the ISOC binding class, you get access to a couple other data types. So one is the C pointer data type, which is actually what we used in those device data attributes. Those are all C pointers. And so what we want to have as inputs and outputs here are the C pointers. So anything that is an array on the Fortran side, an allocatable array on the Fortran side, on the C side, it's a C pointer. We have C integers to make sure that the type conversions are done correctly between Fortran and C. And since they're scalar values, we just pass them by value. So we don't, I mean, most, and pretty much all these kernels, all of these are just used, they're read-only variables anyways, so this is a perfectly fine way to pass those through. Now, there's a little bit of a hitch with doing floating point values. So the self is set up to allow the person who's building the code to toggle between double and single precision. And if I go to the self constants class, you can see how that's done. So if there's basically there's a C pre-processing flag that can be defined called double precision, and it will set on the Fortran side press equal to real 64 from ISO Fortran env, and then on the C side it'll set it to a C double. If it's undefined and we're doing single precision, right, the precision is going to go to real 32, and then C press is going to be C float. So it is important to make sure you have that real type declared in these interfaces if you're passing floating point values through to the C++ side. So that's all we're doing there. But this is what's needed to bind those together. So let's give this a compile and see if this works. Oh, now if you are thinking of contributing to the self source code, one, I'm hoping this is really helpful for you. The last thing we need to do outside of defining the new source code is go ahead and edit. There's a part of the make system called make.include, and this defines all the things that need to actually be built. If you open up make.include, you'll have self F90 sources. Okay, and you can see I've already added self shallow water 1D here. You also, if you start to add GPU kernels, you'll also want to add that to the self C++ sources. And that just makes sure that that CPP file that we just added actually gets compiled during the build process. Okay, so I'm going to go ahead and exit out of this container and clean up my space here a little bit so I don't run out of space, which is good to do every now and then. Those of you who tuned in, I think it was like 6 weeks ago now. I ran out of space pretty quickly doing some of these builds. There you go, 14 gigs just cleared. That's pretty nice. To do the build process, we've tried to make it pretty easy. So the continuous integration process is when you open a pull request with self, we actually use Google Cloud Build to execute builds for various GPUs. So right now we have builds defined for V100s and MI100 GPUs. And they do various precisions. So we have double and single precision. So there's 4 different builds that get kicked off when you open a pull request. And there's a whole bunch of tests that get run. Essentially anything underneath the examples directory is part of the testing infrastructure, which is why it's important to if you're doing an example underneath here, make it short and sweet, and then add some error checking in at the bottom end to make sure that whatever new model you're adding works properly. But Now, in addition to having that remote build system, if you install the G-Cloud SDK on your local system and you add the Cloud Build local binary after you install G-Cloud, you can actually run the build process locally. So if you were to look under the CI directory, there's a couple different YAMLs that define the build process here. So we've got the Cloud Build base, which is actually a build process that sets up a development environment. If you want to just work in a container and develop self live, this will set up a container for you to have HDF5, JSON, Fortran, Flap, HIP Fort, Rockem, CUDA, all that stuff. So you will be able to have the same exact development environment that I'm working with. There's Cloud Build Local, which is the one you can actually use one of those base images to build the application locally and run those tests on your current system. Now, it's not set up to do GPU accelerated tests, but for the most part, it'll get you through a good deal of the CPU side testing. And then we have a pipeline specifically for pull requests, which includes some other stuff, and we'll be adding things like linters to check formatting and things like that. So let's take a look at that cloudbuild.local real quick, because this is what I'm going to be running here in a second to test out everything I just did. So all it's going to do is it's build the Docker image using these following variables below. So by default, it's going to be double precision, targeting a V100 GPU. So the target is set to SM72 for the V100 series. And then the HIP platform we also have to define to NVIDIA. If you did AMD, this would be GFX 906 for the MI100, and then you would change that to AMD. And then you can control what Fortran flags are sent to the Fortran compiler. So if you wanted to experiment with different optimizations, you can do that. There's a couple things that you do want to keep in here, but the default basically enables coverage reporting, which is absolutely necessary for the coverage tests. So, usually I just leave these where they're at. But after building that container, it's going to run this test.h.sh script. So let's take a look at that guy, just to give you an idea of what's going on here. So this is just kind of like a wrapper script that handles, one, finding all the binaries that are created from the example programs. So it loops over for the files in the examples directory from the install, and it runs the test. And after it runs that file, it checks for an exit code. If the exit code is not 0, it's just going to go ahead and kill the whole build process. So it's more of like a fail fast approach. So if something fails right out of the gates, it's not going to go through and execute the rest of the tests. From here, it also handles cleaning up some of the gcov files and kind of merging those together so we can get a clear lumped picture of the coverage report at the end. So at the very, very end, we call gcov-r to merge all those files together and then create an XML. Now the difference between running locally and the cloud builds is the pull request builds with cloud build. They'll do an additional test. So after running those tests, it'll get rid of the individual gcov files and it'll just upload that XML file to codecov so that we can actually use the coverage reports as part of the pull request review process, which is really, really nice to make sure that we're always exercising as much of the code as possible. If you're interested in how to do codecov integrations with Cloud Build, Google Cloud Build, and codecov, you can use essentially Secrets Manager to hide the actual token so that you can basically have this pipeline stored in a public repository without actually exposing the auth token that's used to push to codecov. So you can use Secret Manager to basically define an environment variable. Here it's called codecov token to reference something that's safe to put out there, not the actual value of the token, and then you can reference it above like this with the double $sign out front. So it's kind of nice using Secrets Manager and Cloud Build to get all this done. Sorry for the bit of a tangent here. Let's go ahead and run this local build. So again, we'll use cloud build local. We'll give it as a config file, the cloudbuild.local.yaml. It's weird to me that this dry run flag is always needed, but the default assumption is that you just want your cloud build file to be parsed and not actually executed. But if you set that to false, it'll go ahead and execute your tests. So from here, that Docker file, just to show you what that is. So remember that first step, we're doing a Docker file build. If you look underneath the Docker directory, there's subdirectories, one for base. So this is the base container for AMD or NVIDIA GPUs. The main difference between them is the AMD side doesn't include CUDA toolkit. The NVIDIA side does. So it's a little bit bigger. So let's take a look at since right now we're running the NVIDIA Docker file. All it's going to do, so one, it sets those arguments that we pass through via cloud build. It's going to copy the local directory into the container to this build subdirectory, and then it's going to run through that build process. Now there's some stuff I'm working on to reduce the size of these images. It's not quite done yet, so just hang in there and we'll get that done. But for now, this works for a lot of the testing that we do out of the box. So it looks like I already messed up a couple things. So I have an undefined reference to source shallow water 1D GPU wrapper. So let's take a look at that. 1D. What line was that at? 289. Make sure I spelled everything right, because sometimes that happens. 289. Okay, so let's also make sure that in the so it did compile self shallow water 1D. Let's take a look at that file one more time. There we go. I did not set that to 1D, so I did not have the correct symbol name in the object file, so it was not found. So let's give that another go and see how we do. Now the one thing I'll add here, when we were doing this test, we did add another example earlier today actually. Let me move that up. So I now have a quiet fluid example for the 1D system. So we're just doing the flat bottom right now. What we'll add next is the flat bottom with, we'll add a test with topography in there to show that the same problem we encountered in 2D, we can reproduce in 1D, with the idea being that between today and 2 weeks from now, I'll add in these correction terms from Gassner and Co. 2015 to the flux divergence operator, or the flux divergence calculation method to get that fixed. Because if I could show it's fixed there, then I have hopes for making progress in the 2D solver as well. So let's take a look at how we're doing there. And I'll walk you through this example program. Actually, you know what? Let's go ahead while that's building. We'll go ahead and do the quiet fluid 1D with topography and add that into the system, so you can also see how to add examples if you were to be developing in Self and you wanted to add new methods, new models, things like that, how you could also add your examples in there. So let's go ahead and I'm going to call this guy quiet fluid 1D topography, and let's go ahead and edit that. Okay, so just like we had before, we're going to do domain decomposition. We'll go ahead and get that initialized. Now we're not going to use it because we're not doing MPI in 1D. This is such a small amount of work, it's not really necessary. We'll create an interpolant. Again, we're going to start with the Gauss quadrature degree 7. Later, well, I'm really interested in seeing the difference in the Gauss and Gauss-Lobato quadrature once we get those correction terms in there. I just really intrigued at what's going on. In this case, for the 1D, we actually don't read in Hopper files because Hopper doesn't output 1D files. And instead, in 1D, it's actually really simple to do the mesh generation. We're just going to create a grid, and then in that grid, within each element, we'll create quadrature points. So we'll do a uniform block mesh with linear elements. So like if you did want to have like, you know, in 1D, I could think of a scenario where you might want to like, you know, focus resolution on a particular point. You can do a nonlinear function to kind of squeeze a lot of your quadrature points to one spot. Don't have that implemented yet, but that's the reason why I've left the polynomial degree of the mesh variable here. But we'll go ahead and do linear to start. Then we'll have nx elements, and we'll have the domain from 0 to 1. And we have the same stuff as before. I'm not going to enable GPU acceleration here because we're not done putting those methods in quite yet. But now let's go ahead and do the same thing we had before. We'll do 1 minus 0.2 exp. So if you're wondering how I'm actually able to do string parsing in Fortran, a little bit ago I put up a tool called FEQ parse that allows you to, well, one, provide a character string of an equation, and it'll go through and actually parse that out into using a reverse Polish calculator so that you can do equation evaluation on the fly. It's not incredibly performant, but it's quite convenient if you're just trying to do this kind of work. So any rate, so we'll do x minus, so we'll center that Gaussian hill at 0.5. Let's go ahead and square that. And then we need to divide by the square of the length. So we'll say it's like a, you know, a 0.1 half width. So that would be 0.01 in that denominator there. Okay, so that's our topography. Let's also go ahead and set the topography equal to the total fluid thickness. So the free surface height is also fixed. Oops, there we go. So this would fix the free surface height. Now there's a weird quirk with when you're doing character arrays in Fortran. Each entry in the array has to be the same length, so we have to pad with all this space on the side. It's kind of bizarre, but we just work with it. So that's really the only modification we're going to make. We're going to keep the RK3 time integrator. We'll do a single time step, check the entropy, and then so yeah, the error checking that I typically do is make sure the entropy is not nan. The easy way to do that is so if it's not a number, it can't equal itself, which is pretty nice because then you can just check if the entropy equals itself or not to determine if it's not a number. So if it's a nan, obviously we want to throw an error. If it's infinite, which is basically satisfied by this criteria, if it's larger than this intrinsic huge for the precision you're using, we'll also go ahead and stop. If the final entropy is greater than the initial entropy, for now, I'm just throwing warnings. I'm not stopping anything because right now I am very aware that some of the methods that we're employing don't necessarily satisfy this criteria. And that's acceptable, but it's just something we want to surface during the error checking process. So we go ahead and just throw a warning to screen. And the last thing, for this specific test case, because I know the fluid's supposed to remain absolutely still, absolutely quiet, we make sure that the volume flux, H times U, is smaller than the tolerance. So here, it basically, if H times U is greater than machine precision 0, then we go ahead and throw an error saying that the velocity is not 0, and we will actually stop it there because we do want quiet fluid preservation. So that's the error checking that happens there. All we've done is taken the one with the flat bottom and added some topography to it. Let's see how we did on the testing side. So this bottom one here is for the shallow water quiet fluid block mesh 2D with topography. That one, as expected, has non-zero velocities associated with it. That's what spurred this whole conversation today, was this particular result. I need to check why that entropy is the same, so I'll probably open a bug ticket today, but we'll get to that in a minute. The shallow water quiet fluid 1D with the flat bottom conserved its entropy, and it didn't throw an error, so it must have stayed quiet. So let's go ahead and add this new example. So remember, the new example we have is shallow water quiet fluid 1D topography. So we'll go back into that make.include to add this to the testing. If you look at the self examples list here, we're just going to go ahead and add to this list. Okay, and right now I know that the block mesh 2D topography is going to throw an error because of the non-zero velocity. So for a moment, let's go ahead and actually, you know what? I'm going to leave that error in there. Well, you know what? I'll just have it throw a warning and not completely halt progress, because I think we're aware of the issue and we're actively working on it. So I don't want it to halt our work here. So let's go ahead and actually, I'll just comment it out, because later I'll want to have that in place, because the goal is for us to develop something that will suppress that warning. So we'll just make it a warning for now. So let's do that in the 1D as well. So again, it'll warn, it won't throw a non-zero exit code. Okay. So again, you know, if you're thinking of developing for self, you add new models, it's good to add an example that exercises that model. This is how you do it. You define it under the examples directory, you add it to that list in make.include, and then you can check things by running that cloud build local pipeline, which again, it will only exercise things on the CPU. We haven't quite patched in doing the GPU testing yet, but keep watching what we've got going on. We have some tools that we've been working on, in particular one's called Fluid Run, that basically stands up a research computing cluster on Google Cloud, interacts with the Slurm job scheduler to run tests on GPU accelerated nodes, on multi-node environments like clusters. So if you want to do benchmarking on bigger systems, it's a good tool to use. So stay tuned for that. We'll see how these tests do, and so long as we're able to get through that non-flat bottom case here for the 1D shallow water, we'll go ahead and call it a day. So let's see how we do. Let's go ahead and close out pair view. Yeah, so right now it's just building the Docker image. Should be starting the testing any moment now. So we're getting through all the example programs that it's compiling. Cool, now we're doing the testing. And let's see here. So some of these, I'm noticing I got warnings about the final entropy being greater than the initial entropy. Ah, yeah, those are using the Euler, first order Euler time step. I probably just need to drop the time step size on those to get that resolved. Seems like a time integration issue, because I can do those with RK3 and not have a problem. So that's cool. William asks, just wondering why you're not using the built-in IEEE arithmetic module functions. IEEE is finite, IEEE is nan. That's a good question. I actually didn't know about those. That would be why. I learn something new every day, so thanks for sharing. I guess my question back would be, is there any reason what I have right now wouldn't work? I guess if I had some issues with like portability with what I'm doing, maybe I'd consider it and going with something else like that. But maybe you can help me understand if there's something wrong with the method I'm currently working with. Let me close my camera off here just so we can see this coverage report. So it looks like, actually, it was at 39% before. I like seeing that. We're going up. This is good. Let's take a look at that shallow water 1D. So this is our 2D quiet fluid where we're breaking things. That's okay. Quiet fluid, block mesh 2D, that's okay. Here we go, quiet fluid 1D with topography. Sure enough, I'm able to recreate that error. I got non-zero initial velocity. So this being said, I think the next step here is to add in these correction terms to the 1D solver. Make sure that I can get rid of this, this non-zero velocity in a quiet fluid problem. In addition to those correction terms, I kind of skimmed over it pretty quickly. That paper from, let me actually go ahead and pull it back up here, from Gregor Gassner and co. This paper also pointed out that we need to have we need to have a particular arrangement for the Riemann fluxes. So it's not just adding these additional terms. I actually need to get away from using the local Lax-Friedrichs Riemann solver. And then, of course, in addition, I need to change over to the Gauss-Lombardo points. But like I said, I'm kind of interested in doing a comparison, so we'll be doing that next. So between now and 2 weeks from now, that's what's going on. We'll be putting in this new Riemann solver. We'll be adding in the product error correction terms that are derived from doing this, starting from the skew symmetric form of the shallow water equations. And we'll be switching to Gauss-Lombardo points to see if this resolves the problem. Pretty sure it does. They wrote a paper on it and they have some results that look like it actually gets it right. So we'll be doing the same thing on our side. And from there, 2 weeks from now, we'll be talking about one of the necessary ingredients for getting this resolved in 2D, which is satisfaction of the metric identities. So if you're into differential geometry and some of that stuff, we'll be doing that for 2D and 3D. And I've actually got some corrections to make in the self-geometry class. So if you're feeling ambitious and you want to tackle where you think I might have a bug in my code currently, I haven't put up the issue, but it's related to those metric identities. Feel free to take a poke around, shoot me a message. I'd love to chat with you if you're interested in this kind of stuff. But thanks again for tuning in, and I'll see you guys in 2 weeks.